Next topic is the application of the angular momentum. For moment of momentum, if moving around in the circle, so we call the angular momentum. Before we go to the detail, what is the real condition of this case? This slide it shows the sprinkler that is working from the change from the angular momentum and move it and make it moving around by themselves. And next we're going to apply the Reynolds transport theorem to explain the movement of the sprinkler. Okay. The assumption for our condition, the first one, we assume the flow in 1D uniform distribution of average velocity at any section, and the second is limit to the steady flow or steady in the mean cyclical flow. So that is this term is the change of momentum inside the control volume is 0, and 3 consider around the rotation axis. And next you can see that it is the sprinkler and flow in this direction and flow out from the nozzle. Okay, and this is we draw the control volume. Okay, in this dotted line. Okay, or in this, if you look at the top view, it's a control volume. And the next thing we have to convert the component to analyze the vector. We use the we call the radius and transverse component in terms of the rectangular component x, y, z. We convert to radius is mean radius along the position vector, and transverse is transverse, or we call the tangential component. For example, in this case, v is the v tangential or v transverse, and yeah. And we want to explain in terms of relative velocity. Okay, we have v capital v theta is mean v, this represent velocity respect to the fixed point, and for u is mean velocity of the nozzle, and w is the relative velocity respect to the nozzle. Okay, that is the three different velocity, v, u, and w. Okay, and we apply the control volume. We call the dish shapes control volume. Okay, and this form this Reynolds transport theorem, and R cross F is the change of momentum. Okay, and I will explain that we focus on the tangent component or transverse component of the velocity, but v theta 2 at the point 2 at the exit of each nozzle, and v is the absolute velocity relative to the fixed point. W is relative velocity relative nozzle, and u is the velocity of the moving nozzle. Okay, moving nozzle. So we have this relationship, v equal to w plus u. Okay, and water flowing in the section 1 and flow in the section 2. Section 1 is at the bottom, at the bottom of the dish shape, and flow out at the surface of the cylinder. Okay, we fix and use non-deformed control volume because this shapes control volume and apply for the control surface. Okay, so we got this equation R2 v theta 2 times rho v2 a. So this comes from the, because of angle is 0, so we got v theta 2. Okay, and we got this for the change of momentum on the surface, and m dot is the mass rate of change through the both nozzle. And to explain the the cross vector between R cross V, we have two cases. The first case is if the tangential velocity v theta 2 and u2 are in the opposite direction. Say that in opposite direction, we expect that r cross v is negative. Okay. In another case, if the angular velocity is on this direction and r cross v is a positive, if v theta and v u2 are in the same direction. Okay. That is two conditions. Okay. From the transport theorem, we can cancel this term. This term is equal to 0 because nothing changed inside control volume, and if we convert from unit vector r to a transverse unit vector, and because of theta is 0. Okay, so we got this equation: t sharp angular velocity, angular momentum for spinker is equal to this term, and negative sign because of the opposite direction to the spinker rotation, and come up with the next term. If we time the omega or the angular velocity with the sharp, with the torque, so we got the we call the sharp power. Okay, w dot sharp is sharp power. So it means the sharp power is equal to u2 times v theta 2 m dot. Okay, it means this u is equal to r2 omega. Okay, negative because of the work is out of the control volume. And finally, we got this term from the transport theorem in case of we have inflow in and flow out. Okay, and if we convert this term to work, so we got the next term, and this term we got the the work from the sharp power from this sprinkler. And since we have theta equal to u, so we got another equation of the sharp power. Okay, that is we have two conditions for positive and negative sharp power. Okay, for positive sharp power is mean power is into the fluid in case of the pump, but for the negative sharp power is out of the fluid, so we call the turbine. And this is for the condition that is the time v theta is greater than is positive. Okay, and in this case that the theta is less than 0 or negative because of v and u is in the opposite direction. But in this case we expect that v theta and u is in the same direction.